So for the kinetic equations, they're all based off of 1. So we know that acceleration is always g, right? So let's transform this into a function where acceleration is a function of time. That means if we integrate both sides, we get the integral as a function of time, which is velocity as a function of time, is equal to the integral of g with respect to the change in time, which is just gt plus c. We'll call this constant 1. So now we have an equation for the velocity in terms of time. And then if we integrate this position, we'll call S in terms of time, which is the integral of in terms of the change in time, which gives us 1/2 gt squared plus c1t position versus time. We need to give these values actual meanings. So our first constant we found from our velocity. So c1, or the initial velocity, which you can also call u, and our second constant we got from integrating in terms of velocity. So that's our initial position, which you can call s naught. So here our final equation becomes s is equal to, I probably like this, s naught plus ut plus 1/2 gt squared. And you also bring this here, you get that the change in s, which is equal to ut plus 1/2 fundamental equation we have. Now from here we can make a bunch of other equations. Using this, all of these equations here, we can also see that some generalized equation can be made. So velocity, or average velocity, is the change in position over the change in time, which you can write as s minus s naught over t. And so that means if you multiply both sides by t, you get pt is equal to s minus s naught, which then gives us s is equal to s naught plus st, which you might have seen as d is equal to d, or you've probably seen as x, not sv, so velocity time. And this also goes for the y-axis. Usually there is, which is why you add the term plus 1/2 gt squared. So that's kind of a link between these two equations. Could also do, we made this equation, we can make this equation. We made this average velocity. That's just the average of anything. So we'll say the average of any number or any value. So we'll say function. The average of any function is equal to over 2. So that's why it applies. Oh yeah. Acceleration is the change in velocity over the change in time, which means you can also write it like u over t, or the change in t, which means we get that a change in t is equal to v minus u. So we also get the other equation. V is equal to initial velocity plus acceleration time. So we want to make the equation v squared is equal to u squared plus 2as. So for this one, it begins with starting with this equation, v is equal to u plus at. Now what we want to do is replace t. Since we know that velocity is acceleration is change in velocity over change in time, we can see that the change in time is equal to change in velocity over acceleration. So we substitute that into here. We get that velocity is equal to u plus a. So these guys cancel out. So we get here v is equal to u. So v is equal to u plus, which is equal to vu minus u squared over a, equals the change in s, plus 1/2. One of the a's cancel out. We get v minus u squared over a. We can multiply the entire thing by a. We get a change in s is equal to vu minus u squared plus 1/2, and we expand this quadratic, we get v squared plus u squared plus minus 2vu. Yes. Okay. Then from there we get vu minus u squared plus, and we can expand the 1/2 into each term, so we get v squared over 2 plus u squared over 2 minus vu. So now these two terms cancel out. We get here minus 2, we'll say 2 over 2 u squared plus 1/2 u squared plus 1/2. These guys cancel out, so we get positive 1/2 u squared plus 1/2 v squared is equal to a change in s. We multiply both sides by 2, we get 2a change in s is equal to u squared plus v squared. Now we isolate for v squared, we get v squared is equal to, one of the negatives should have canceled out. Oh, there you go. So this should be negative. So we get in the end u squared plus 2a change in s. There you go. That's the final equation of that. We can also make another equation for this, for a specific situation. So let's say you have a projectile that begins from the ground, ends from the ground. A regular projectile equation, or question. So you know it begins with initial velocity, v, we'll say u, and it has two components, ux and uy, to give you the product, u. So from here we can say that a constant ux, because there's no acceleration along the x-axis, but you gradually lose and then gain velocity. So we'll say this is v, due to the acceleration of gravity. So initially going up, since this is still this way, vx, your final product velocity is that way. So we can make two statements here. You can say that the initially has two components there, uy and ux. And we know the equation v is equal to u plus at. So we can say along the x-axis, you have initial velocity x, the acceleration along the x times the time along the x, I guess. Since you have no acceleration along the x-axis, it's 0, because you're neglecting drag force or any wind resistance. This becomes vx is equal to ux. So the distance along the x-axis, we'll say sx. So we know there's some velocity along the x and y-axis. So using this equation, s is equal to s naught plus ut plus 1/2 at squared. So for position along the x-axis, we have the initial position along the x plus the initial velocity along the x, time along the x-axis plus 1/2 acceleration along the x-axis, and the same time along the x-axis squared. So there's a few simplifications we can make. We start at point 0, and also there's no acceleration on the x-axis, because ax would otherwise be the drag force or wind resistance, but we don't count for that. Our position along the x-axis is just ux tx. Then we can also say for y-axis, tx, or ty, sorry. Now the acceleration along the y-axis is gravity. Sy is equal to, these two equations are just, you can use it anyway. They're always true for any question you have no drag. So now let's make an actual big equation. So with this, what we can say is, this equation is the position So we have these two equations, and we can make something called the trajectory equation is no longer a function of time, but it's a function of x itself. So given some position along the x, we can find where we are along the y. So to find that, we actually have to replace minus 1/2 g/ty squared. So what we have to recognize is that the time along the y is the same as the time along the x. You can't travel for longer along the y and then less along the x. That makes no sense. Since time is linear, the same steps along the y and the x correspond to the same time interval. Ty is equal to, we can derive from here, since x is equal to uy, so substituting back into here, we get that y is equal to x over ux squared. So then we get x times uy over ux minus 1/2 gx squared, 1 over, going back to the graph, if our actual u, our initial velocity is u, v naught is u, the components vy or uy is equal to, given a launch angle theta, uy will be u sine theta, and vx will be ux, which is equal to u cos theta. So plugging that back into here, we get that y is equal to x u sine theta over u cos theta minus 1/2 u squared. And what we can also do is say that this y is also the change in y. Same thing, it doesn't matter. But that distinction helps for the next part of this equation. So here, these two cancel out. These two form tan theta. So we get that the change in y is equal to x tan theta minus 1/2. We'll say actually gx squared times 1 over 2u squared. So what we can see here is that this equation, y, is a function of x and possibly u and theta. So to ever use this equation, you need the launch angle, you need the initial velocity, and the position along the x. So at any point to use this equation, you know at least those three, or you just need y, you can figure out the other one. Now with this, you can actually give it the new name, because we've completed it. So this is the trajectory as a function of x. Now with this, we can actually make another equation, which is called the range. So we'll make another diagram here. What trajectory allows us to do is that, given some graph and some flight path, we can figure out any point like this. We can call this a sort of, we'll say, okay, let's straighten this out. So this distance I traveled is we'll call this a partial, in that if it had continued, we would have gone over and ended up here. So it's missing sort of this portion right here. So this partial path is known as if it had gone the entire part, this complete part is called the range. So if you had a rocket that went through its full path, it went through its full range. And for us to actually figure that out, we can actually make an equation from this. So let's rewrite the trajectory equation. T is a function of x is equal to x tan theta minus gx squared times 1 over 2 u squared, u squared cos squared theta. There you go. Now what we know from here Going back to what I said here, the change in y, tx is the same as the change in y. So that means if you start and end at the same point here, that means our change in y is 0. So what we can say here is that 0 is equal to x tan theta minus g x squared over 1 over 2u squared cos squared theta. Now what we can do is say let x equal r. And why is that important? Well, if x is the distance along the x-axis and we want to account for the full range or the full distance, we can denote that as r. So let's go here. So now we see that 0 is equal to r tan theta minus g r squared times 1 over 2u squared cos squared theta. Now let's isolate for r. We bring it to the other side. We get that tan theta is equal to gr times 1 over 2u squared cos squared theta. Now what we see is that gr is equal to 2u squared cos squared theta tan theta. Now we can say that r is equal to 2u squared over g cos squared theta tan theta. Now you can leave it like this, but we can actually do something else. So here we can rewrite this as u squared over g times 2 cos squared theta tan theta. Now let's focus in on this trig part. Cos squared theta is just cos theta times cos theta. Tan theta is sine over cos. So these cancel out. And of course, there's a 2 there, so we get that 2 cos theta sine theta. Now we should recognize that if you flip the position of that, you get that's 2 sine theta cos theta, which is one of the double angle identities. Sine 2 theta is equal to 2 sine theta cos theta. So knowing that, we can see that our final range equation is r is equal to u squared over g sine 2 theta. And now what we can see from this equation is that r is a function of initial velocity. G is always constant. If g wasn't constant, if you had some different acceleration, for a generalized equation, this would be negative. But we also always know the acceleration, and it's also the function of the launch angle. We'll say theta L. And something else you can always see is that sine begins at 0, midpoint, max, midpoint, 0. There. Okay. Actually, it's like that. Oops. There you go. So sine looks like this. If it's sine 2 theta, that means our entire period is just 1 pi. 1 pi. So, okay, adding more logic to this. The range here is equal to u squared over g sine 2 theta. Right? So what we can see here is that gravity, we can say, is always 9.8. And u squared is really, even if it's negative, it's squared, so it's positive. So u squared over g is always greater than 0, or also greater than 1. So our goal with this equation is always to maximize this value. So in order to maximize this value, we have to minimize this value. What that means is, for us to get the maximum range, this value has to be at least 1, or as close to 1 as it can be. Because if it was less than 1, let's say if it's between 0 and 1, if it's some fraction, we're only going to get some fraction of this velocity, or this range. So we want sine theta equal to 1. So that means 2 theta has to equal arc sine of 1, which is equal to pi over 2, which is 90 degrees. And also, since it's sinusoidal, we want to include every single theta that can be possible. So that's why if you want a generalized term, we can get that pi over 4 plus 2 pi n. Of course, mathematically that makes sense. And of course, we can say that n is the element of the integers. Mathematically that makes sense. But looking at it in a physics perspective, if you throw a ball at big neck. Okay, if you throw a ball at 90 degrees, just throwing it up. If you throw it at 180, or sorry, not 180, at 0 degrees, you're just throwing it straight at 180 degrees. So let's say like this, you're throwing it backwards, which has no use case for us in terms of physics, because then we'd have to, going back to the graph, we'd have to look at it in the opposite direction. So let's say this was thrown this way. That has no use for us. So we know that this is true such that theta is between 0 and 90. So what that means for us, finally, because we have a stretched sine function, you have another 45 degree. So one here and one here. Okay, so basically the final point is that if you ever have a problem telling us that objects being thrown at different angles, but they have the same range, these two thetas, so say theta and phi, sum of theta and phi will always be 90 degrees. Because that 90 is what makes our function equal to 1. Because all that's saying is that 2 theta has to equal 90. Of course, theta equals 45. So that's telling us that's our maximum to give us the maximum range. But in general, as long as 2 theta, or this inner function part, is 90 degrees, then you'll have the maximum range achieved. So in short, if that made more sense, if you have a problem and it tells you 2 objects are thrown and they both reach the maximum range, the sum of the 2 will always equal 90 degrees. So if you had one of them and you wanted to find the other, just 90 minus that other one.